So as I said, today we're going to finish our discussion of cache coherence, and then we'll talk about coherence's tricky pal, memory consistency. Okay, so to refresh our memories about where we were, we're talking about, definition of coherence. And the definition of coherence, we said, was that we wanted to have a memory system that, even though we had these multiple caches that shared the cached memory locations from a shared address space, if we looked at any particular address, what we want to see is that all of the reads and writes made to that address by all the processors can be ordered in some sequential order, such that the ordering corresponds to the program order issued by any of the threads in the processor. Okay, so that's the first thing. Second thing we want is we want to make sure that in this sequential order, that the value that you read, it was the value that was last written in the sequential order. So these are the two things that we want to maintain in a coherent memory system with caches. Okay, so we said that in order to implement this, there were two invariants that we needed to maintain. First, the idea of a single writer, multiple reader invariant, right? So we can sort of abstractly divide the access to any particular location into these epochs. And these epochs could be a read-write epoch in which only one processor has sole access to the cache line, or a read-only epoch in which multiple processors can read. So it's read-only, but multiple processors can share the line. And the idea of the data value invariant was that, the value that you see in the read-only epoch is the value that was last written in the most recent read-write epoch. Okay? Everybody understand these two invariants? Okay, we're going to come back to them in just a moment. So we said the issue that we have with we could implement cache coherence with write-through caches, but that was not, had performance problems because every write that the processor makes appears on the bus, and the bus becomes a bottleneck, a performance bottleneck. So in a write-back cache, right, we have this problem that each individual processor has its own cache, and if everybody is writing into that cache in a write-back fashion, then of course we have an incoherent system, right? So the question is there are two questions. One is, when as a processor do I have the permission to actually perform a write? All right, so, and the way that we want to indicate that a processor can perform a write is by having a modified or dirty state, right? And so the idea is that, the only one processor should be in the modified state at any point in time. And then the second question is, okay, so I have got this data in my cache, and some other processor wants to read that data, read that cache line. So the question then is that, who should provide the data to that processor? And it should be the owner of the cache line, which is typically also the processor that has the cache line in modified state. All right, so let's kind of see how we actually implement a cache coherency in write-back caches. And what we want is an invalidation-based write-back protocol to maintain these two invariants that we've defined. Okay, so the idea, as we've already pointed out, is that you want to have a single line in the system in modified state at any point in time, and that the idea is that the processors can only write when they've got the cache line in modified state, and then you have to have a way of getting the data from a cache that has it in modified state to other caches that want to read that data at some later point in time. Okay, so let's see how this works. So we reminded you that the idea, we talked about a cache line. We said there's the data component and the metadata, and part of the metadata is the tag that indicates the line, the address of the line that is contained in this cache, particular cache line, and then the dirty bit indicating that the data it has been modified in the cache, and then the line state, which is going to be used in the cache coherence protocol. All right, so we talked about we briefly introduced the idea of a modified, shared, invalid, write-back invalidation protocol. And so what we want to make sure then is that with this protocol that we can maintain the two invariants to implement cache coherency correctly. So there are three line states: invalid, right, which basically means that the cache line is not in the cache, right? So it's the idea of it's not there, or it's of course if you access that cache line in an invalid state, it's going to be a miss. Then there's the shared state, right? That says the line is valid in one or more caches, and the important thing to remember is that memory is up to date. So whenever a cache line is in shared state, memory is always up to date. And then there's the modified state, and in this state, the line is valid in exactly one cache, right? So only one cache in the system has the cache line in modified state, and also means that the dirty bit is set. Another way of thinking about this is it's exclusive, right? So only one cache in the system has the cache line in that state, and so you can think of it as being exclusive. Okay, so then there are two operations that the processors can make. They can make reads and writes to cache lines, so processor reads and processor writes, and then there are three coherence bus transactions that are the result of these reads and writes that get made by the processors, right? There's a bus read, which says, get me the line because I want to read it. Bus read exclusive that says, get me the line because I want to actually modify it. I want to change it, so I want it to get it into exclusive state. And then bus write back, which says, hey, there's a dirty line in the cache that's going to be replaced, and I'm going to write it back to memory. Okay, so let's see how these operations get implemented in a cache coherency protocol. So here is the cache coherency protocol state transition diagram. So we have the three states: invalid, shared, and modified. And we have the operations that are made by the processor and the subsequent transactions that come from the bus. So the way to read this state transition diagram is that each of the arcs is labeled by a A-B action pair or transaction pair. And so the A is the initiating action, and then the B is the resulting behavior or resulting action taken by the cache controller. And the way to think of it, the way to look at it is that the green labeled actions are initiated by the processor, and the red are initiated by the bus. Okay, so let's look at this transition diagram in more detail and dissect all of the different transitions. Okay, so let's start with the processor initiated arcs. So let's assume that the cache line is not in the cache, or it's an invalid state, right? So if a processor does a read, what is the action of the bus? What's going to happen on the bus? So of course, if it's invalid, this is a miss, right? So you can think about any action that the processor takes that results in a bus transaction. Think of it as a miss. Okay? All right. So we start out in invalid state, and we issue a processor read, and this results in a bus read, right? It says, get me the cache line because I want to read it, right? So that means that the line has to move from invalid to shared, right? Okay? And then if the application then does a write to that cache, to that address which is contained in a cache line, in the cache line, then it's going to issue a processor read, and what's the result on the bus is a bus read exclusive, right? And so bus read exclusive says, hey, now I need to move the state of the cache line from shared to modified, right? And modified means that, of course, that this is the only cache line in the system that is in modified state, okay? So then if we have the cache line in modified state and we issue reads and writes from the processor, what happens? Nothing, right? These are hits, right? These are hits, so that's indicated by sort of nothing in terms of the B action. And so you can do whatever you like in modified state, and there are no bus transactions that result from that, right? Okay, so what happens if we go from, if the processor, the cache line is invalid, and we issue a processor write? You go straight to the modified. Okay, good. All right, so this is what happens from the processor's point of view on an individual cache, right? But then all the other processor cache controllers are snooping on the bus. So whatever transactions show up on the bus of a single processor, remember, all the other processors get to see. And they're snooping on those. And if they see a transaction for an address contained in their cache, then they need to take an action, right? So let's look at those actions. All right, so, we've got a few more processor initiated, well, one more processor initiated action. So if we're in the shared state and the processor does a read, what happens? You stay there, and any bus transaction? No, okay? So what happens if we're in the shared state and we see a bus read transaction over the bus? Nothing. Okay, it's a shared state. So what does that mean about the state of the cache line in the system? Yeah.
It's the same across all the caches.
All that have that line in shared state. So any cache that has that cache line in its cache is going to have it in shared state, right? Okay. Is it possible for any of those caches to have it in modified state? No, right? All right, so suppose we see a bus read exclusive transaction on the bus for a cache line in our cache. Then we need to make this transition from shared to invalid, right? So that would be the case where some other processor wants to write this cache line. So what happens to the state of the cache line in my cache? It goes to invalid. All right, so if I see a bus read, I'm in modified, what has to happen? So we know that if we've got the cache line in modified state, and it's a write back cache, so we have the only valid copy of the line in the system, right? So if you see a bus read transaction on the bus, then what has to happen? Well, I need to supply the data in my cache, right? So I see the bus read, and the response is a bus write back. Everybody follow that? So yeah.
And that also takes us to back in shared state.
Yeah, and then transition into shared state, right? Because we know that it is not possible for caches, for cache lines, for any other cache to have a cache line in its cache if it's in modified state, right? So it's got to move to shared. Yeah.
And the write back is writing back to memory.
Correct, right? So you update, you're giving the data to the requester, right? But you're also updating memory. Because whenever you're in shared state, memory is always up to date. Yeah?
What if there's contention, what keeps us from thrashing back and forth in different states?
That's what you're going to do all day long. Absolutely. That's what's going to happen. And what are you going to see in terms of performance? it's going to be a lot worse, right? You're going to see lots of cache misses, and we'll look at a case like that in just a moment. All right. What about bus? We're in modified state. We see a bus read exclusive, right? That means some other processor wants to read this cache line. We have it, the only value. So we have to supply the up-to-date, the most recent copy of the cache line. So it's got to be a bus write back. But then we also have to move to invalid state. Okay, everybody understand that? So let's do an example just to reinforce what we just talked about. All right, so cache coherence example. Here are the processor actions. By the different processors. They're all, which simplify things, we're just using one address. All right, and so what we want to look at is the state of the cache line in the 3 caches, the bus transaction that results from the processor action, and where the data comes from. Okay? So, processor 1 does a read. What's the bus transaction? I suppose I gave the game away here. What's the bus transaction? Bus read, okay. What's the state of the different caches? Huh? Shared. Shared in processor 1's cache, and it's invalid or not there in the other caches. Where's the data going to come from? All right. Processor 3 does a read of X. What's the bus transaction? What's the state of the caches? Okay. So, and then where's the data coming from? Remember, shared, when you're in shared state, the data always comes from memory, right? And it's just to keep things simple. We can imagine some other scheme, but then we'll see an example where should you get it? If 2 caches have it, who should you get it from? Right? All right. So processor 3 does a write. What's the bus transaction? Bus read exclusive. What's the state of the caches? Modified in processor 3 and invalid in processor 1, and the data comes from memory. Okay, processor 1 does a read of X. What's the bus transaction? What's the state of the caches? And where's the data coming from? Processor 3's cache. Okay. Processor 1 does a read of X. Where's the what bus transaction occurs? This is a tricky one, right? There's no bus transaction here, right? It's a hit. Yeah.
Data's coming from P3. How does memory know that it doesn't need to reply to that read transaction?
How does memory know? Because it knows that the state of the, it sees the state of the, basically the processor that has the cache line tells memory to hold off. Yeah, that's the way to think about it. Yeah.
What if you had a P1 row after the P5?
Where? This one?
Yeah.
Here? If this is a write, you tell me what happens. What's the bus? If P1 does a write, what's the bus transaction?
Bus 3x.
And then what happens?
Then just P1 copy from P3.
Yeah. So in that case, it's the same thing, right? The data is going to come from P3, but what's going to be the state of the caches?
But P1's going to be having
Yeah, right, exactly. But the data moves, right? Okay, so in this case, nothing happens in terms of the state. We don't have a bus transaction. And where does the data come from? Its own cache, right? It was a hit. Okay, in process do does a write of X. What's the bus transaction? What's the state of the cache? Right. And then where's the data coming from? What? Memory, right? Yeah.
Is there functionally any difference between invalid and just the dash?
Well, not Dash says we never saw it at all.
Right.
But functionally, as far as the processor accessing the cache line, it's the same thing. Yeah. So essentially, if it was a dash, then it would be a cold miss, right? As opposed to, hey, it got invalidated. Okay, so notice that we do have the single writer, multiple reader protocol, and so the question is, why do you need this transition from modified to shared? Why is that important? Yeah.
I guess to indicate that the cache line is back in memory.
Back in memory, and what else? Yeah.
Indicate that another cache or another processor is the one that can modify it. So you need a transition.
Modified to shared. Why do you need modified? For instance, this case. Why is that important? Yeah.
Well, otherwise, it would have to go to invalid, right?
Right. Well, you need to remember. We can only have one. Remember, the invariant we're trying to maintain is single writer, multiple reader, right? So we need, in order to track that transition, we need the transition from modified to shared. Okay. So the other thing to know is that communication increases memory latency, right? So we saw that here is that because P3 did a write to X. P1, which had X in its cache, now has to do a bus transaction, right? Which is going to take much more time than hitting in its cache, right? And this is the case where you had the cache hit, right? But if you had an intervening write, then it causes extra cache misses, and so of course you're going to lose performance. So, just to reinforce this idea of how the MSI protocol maintains cache coherence, let's think about the cache coherence invariance. And so, how do we maintain the single writer, multiple reader invariant? Yeah.
That's that transition from modified to shared that we were talking about.
Right. And then, so that's how in shared state, you have multiple readers. Right. And how about the single writer?
Only 1%.
Only one cache can be in the modified state at any point in time, right? Yeah.
I was going to say that, yeah.
Good. Okay, what about data value invariant? Tell me about that. So how do we maintain the right serialization?
We go through the bus every time, so the bus acts like the serializer.
Right. And what about the data value? How do we make sure that the data is moved from the read-write epoch to the read-only epoch? Yeah.
We go to the shared state, so we know that nothing is.
You go to the shared state, yeah.
I guess it's like you use the processor that modified it, like that's the source of the data.
Right, and that is maintained with the bus write back, right? So the bus write back, whenever you come out of the modified state, you as the cache that had the line in modified state have to provide the data for the cache line. Yeah.
So the processor makes right, we is in shared or modified state, and then another processor tries to make the write this memory. Yeah. We'll only get out of the first processor out of modified state after that processor's done writing. But you can't be like mid-write and then it's like.
Well, it's gonna complete its write. If it gets the line, basically the bus is going to serialize all the actions, right?
Right. It'll complete.
It will complete,
Okay.
modify its cache line, and then it'll be time to write back to the next processor that wants to write. So the line could bounce all the way around, but essentially every time that you got exclusive access to the cache line, you get to do a write. Yeah.
Where is the logic process that's used on the bus transition?
Yeah, well, this is hardware that's implemented, in the cache controller, right? Yeah.
Is
Each
each processor has its own cache?
processor has its own cache controller connected to the bus.
And then is there also maybe like a logic across them, like the track?
Well, there's not logic across, but there is some access control logic that says who gets to go next, right? All right, so, yeah, and the bus realizes the transaction. So these are the two statements that we just made. Okay, any questions about how this works? All right, so in summary then, the way that we're going to do MSI is we're going to keep these three states. We're going to make sure that only one processor can be in modified state. And in modified state, this is the only processor that can write in the system to a particular cache line. And if you maintain this invariance by having this bus which serializes all the transactions in the system, and make sure that we move from the state in one cache to the next in a serialized manner. Okay, so this is the way the MSI works, and the result is, of course, it keeps the caches coherent, but it has a downside, and that is whenever you want to read a cache line and then write, sometimes going from shared state to modified state is called an upgrade. So this is the term upgrade. Okay? But the problem is that you now have two bus transactions. You have the bus read, which is a miss, and then you have a bus read exclusive, which is also a miss, to upgrade the cache line from shared to modified, right? And so the idea is that you can optimize the MSI protocol by adding an exclusive state, right? This is called the messy invalidation protocol, not to be confused with the Argentinian international soccer superstar. And the idea is that now you're decoupling ownership from whether you have the line in modified state, right? So what does this mean? What does exclusive mean in this context? What's another way of describing the exclusive state? Yeah.
Well, it's just that the line is not dirty, but all of that processor has.
Right. So it's clean, exclusive, right?
Yeah.
Right. So it's clean, but it's but only one cache has it. All right. And so the idea then is when you read a cache line that is not shared by any other processor, instead of bringing it into the cache in shared state, you bring it in exclusive state because no other cache has it, right? Okay, so you go from invalid to shared would be the typical case if the line was shared, but if the line were not shared, then you could go directly to exclusive state. And now the upgrade can be made without doing a bus transaction, right? So it's not a miss, it's a hit. And in which case, it's going to be a lot more efficient, right? And so, given what you know about the MSI protocol, you can fill in the rest of the transitions, right? And so I'll leave that for you to look at in detail at your leisure. Any questions on MESI, messy protocol? Yeah?
Why is it more efficient than just taking that far left path, just the bus read X?
Where?
Sorry, other off the,
This one.
yeah, the bus for that.
So that's if you did a write first.
You want to read?
I want to read first and then write. Yeah. Okay, questions? All right, so the problem with buses, of course, is they don't scale, right? You've got a single set of wires that everybody's sharing, and so that means that every transaction is seen, for every cache line, is seen by all the processors, right? Even the processors that don't have that cache line. So that's one problem. One problem is, of course, all the processors sharing this interface, between the caches and memory, and so you're going to run out of bandwidth. And so the other issue is that you're serializing all of the bus. So you're serializing the transactions to all the cache lines, whereas we really only need to serialize actions to a particular cache line, right? And so one way to potentially make a system that's more scalable is to use the idea of a directory, right? So the idea of a directory is it stores information about which processors actually have this particular cache line in their cache, right? And then, given that information, you can send invalidates or you can communicate with just a set of processors that need to know, as opposed to all of the processors in the system. And so this makes it possible to use interconnects that are more scalable. So instead of having a bus, you could have a network or a ring or something that doesn't require this ability to broadcast information and serialize all of the transactions in the system. You only need to serialize transactions to a particular cache line. So that's the idea of directories, and so that's what's implemented these days on most multi-core processors, right? For instance, the i7 that's used in your MIF machines, right? So you've got a ring interconnect, and the ring interconnect is not a broadcast interconnect, and so snooping won't work here. And it's also, of course, more scalable. But what we have is we have a directory associated with the L3 cache, right? For this to work, we have to guarantee that every cache line that could be in any of the L2s will also be in L3. This property is called inclusion. Okay, so L3 is an inclusive cache, right? And then we got for each of the cache lines in the L3, we have a directory, right? And the directory in this case is you can think of it as 5 bits, right? So we have a bit for processor 0, a bit for processor 2, a bit for processor 1, 2, and 3, and a dirty bit, right? So the idea then is that if you're in shared state, then multiple bits would be on, right? So this would indicate that a particular cache line is in cache for processors 0, 1, and 2. And so if a write came in, then we would know which processors to send invalidates to. Okay? And then if the cache line were in modified state, then of course there would be a bit set, the dirty bit would be set, and then just one of these bits, say bit for processor 3, would be set, and the rest would be zeros. Okay? Indicating that only one, we know that whenever we're in modified state, only one of the caches in the system can have the cache line. So the directory then is more scalable, but of course you need extra information associated with some place in the memory system that keeps the directory, right? And there are all sorts of schemes for implementing directories more efficiently, but you get the idea. All right, and with a directory-based cache coherence scheme, you can scale to tens of processes, maybe even hundreds of processes. Okay, any questions? All right, so what are the implications of cache coherence to the programmer? So the issue, of course, as we've already talked about, is that when you have communication in your application, since you're sharing memory and the processes have caches, and the way that the caches are kept coherent is by using cache coherency mechanisms, what's going to happen is that the distribution of misses, of accesses in your system is going to change, right? So what's going to happen is that you're going to have an increased number of cache misses at the different levels of the memory hierarchy. And if you have a NUMA system, have we talked about NUMA systems? Okay, so NUMA systems, so if you've got multiple chips or multiple sockets in your system, right? Suppose socket 1, let's call this CPU 1 and CPU 2, and these are different sockets. They have DRAM associated with them. DRAM 1, DRAM 2, and then there's some interconnect. And remember, inside these CPUs are multiple cores, right? So the idea is that you have much higher bandwidth to your local memory than you have to, so CPU 1 has higher bandwidth access to its local DRAM than its remote DRAM, right? And to a first order as an application programmer, you could care less because you'd rather not have to deal with this issue. But if you actually want to get to maximum performance, then you may want to have the operating system allocate data such that you have better, so that data is accessed more often by the processor where that data is local. But anyway, from the point of view of the access patterns, NUMA accesses cost you more, right? So if we're looking at, for instance, the Core i7, we see that an L3 hit is 40 cycles if it's unshared, it's 65 cycles if it's shared, and it's almost double, 75 cycles if it was modified in a different core, right? So essentially, because you have communication, and because you've got a cache coherency protocol that is managing this communication, communication means extra latency, extra time, and it also changes the distribution of misses, right? And so if you think about the average memory access time of your program, it's going to be the frequency of access of a particular part of the memory hierarchy times the latency of access. And what happens when you go from a uniprocessor application to a multiprocessor application is that you change the distribution of accesses such that you access levels of the memory hierarchy that have longer latency, right? So the result, of course, is your average memory access time of a multiprocessor or a parallel program is going to be larger than a sequential program, right? And so that is the impact on the performance of your application of the communication overhead, right? And you can see the latencies as shown by the Core i7 data that I've shown you here. If you want to kind of analyze this, right, you can use system tools, right? So, for instance, if you're on an Intel processor, you can use Intel vTune, and Intel vTune will interrogate the performance counting hardware on the processor and tell you about cache misses and to some extent communication. If you're on an Apple M1 machine, on a laptop, you might use Apple Xcode instruments to get a similar source of information to tell you about what data structures are causing cache misses, and then, you know, based on your knowledge of the application, you can improve the locality to improve performance. So one of the things that happens when you have caches and cache lines and sharing is sometimes you get sharing where you don't expect it. This is called false sharing. So let's look at an example of how and where this can happen. Suppose I've got an array of integers, right, based on the number of threads I have in my program. And so the question is why I could allocate it, the per thread variable as shown in the first instance, or I could create a struct that looks like this in the second instance. So can somebody tell me why this second instance might be more performant? Yeah.
I mean, the data will be local to each process.
What data will be local to each process?
Like, you're not sharing, like in the first one, the first variables are allocated like in a different cache, and so I guess, I don't know, maybe it seems to me that the second one would be in the cache that's local for each process.
Can somebody expand on that? Yeah.
In the first case, you could have multiple instances of the counter, like multiple locations going to the same cache line. Right. Whereas in the second one, you ensure that each one is exclusive to a line. So there's no contention. Though in theory, everything is implemented because we crush it into a cache line. In the first case, we're going to have communication.
Exactly right. So we all remember cache coherence does communication on the basis of cache lines, right? So ideally, if you could do it on a per word or per byte basis, if you could do coherence on the per byte, it would be very fine-grained. It would be great for the application programmer, but a nightmare for a hardware designer. But the result of using cache lines is that we have what is called false sharing, which is sharing where you don't expect it, right? So, for instance, if this is the worker function, which is essentially just going to, add increment the per thread variable, right? And we could implement it, so we fire off a bunch of threads, and we time the two instances. And in the first case, on a 4-core system, it takes 14.2 seconds, and in the second case, it takes 4.7 seconds, right? So dramatic, of course, this is a contrived situation, but false sharing can really impact your performance if it's happening a lot. Okay? So, and that's an example where, of course, these thread, the data is actually all independent, but because of the fact that the multiple local threads variables are landing on the same cache line, we get this unintended communication called false sharing. False sharing also happens in numerical applications. If you've got some sort of grid application and you have cache lines that cross a grid boundary that's been assigned to different processes, then you can get false sharing. Here's some data from some old benchmarks that were first written at Stanford probably around 30 years ago, but are still being used. And so this is data which is showing miss rate for different cache line sizes, for different types of misses, right? So you've got cold misses, which we talked about, capacity conflict misses, which we've talked about, then true sharing misses. This is where the data is actually shared. and full sharing misses where the data is only shared because it happens to land on the same cache line. Okay? So the first thing to notice is that, there's a significant amount of spatial locality in truly shared data, right? Because you see, as you increase the cache line size, the amount of true sharing misses gets reduced. Okay? But take the example of radiosity, we see the amount of full sharing misses increase. Okay? With cache line size, right? Which is, you'd expect if it was truly just, you'd expect it to go down if it was giving the increased cache line size, but it goes up because of full sharing. The extreme case is radix sort, where you have a dramatic increase in full sharing due to the way that the application is written. Okay? So, of course, the longer you make the line size, the worse the full sharing gets. Right? So you can imagine if you got to a virtual memory size line size, the full sharing would be terrible. Right? So remember way back when I said, so one of the ways of doing coherence is potentially using a virtual memory page and the operating system. So forget about the software overhead. Your full sharing problem is going to be horrible. Yeah?
If you were intelligent enough and always use SIMD operations, which were the size of the cache line, because it's simply, then you would not have this problem, right?
Well, the full sharing has everything to do with the size of the cache line and the data that's being accessed by the different processors. What happens, inside the processor is kind of not relevant, right?
Yeah. Is it like, can you always guarantee that you can reduce the false sharing to a large degree programmatically? Or is it just how it is?
Well, you can always do it programmatically if you space the data apart such that But then aren't you But you may be increasing you may be wasting space.
Yeah.
Right. I mean, so you certainly can make sure that you space things apart such that full sharing doesn't occur. But there may be other reasons. Maybe you have phases to your application, and at some point you need to switch things around, and it may not be convenient to organize things in ways that minimize full sharing. But you should be aware of it. Okay, so in summary then, of course, the reason that we've got this coherence problem is that we have this shared address space being implemented by independent separate caches, and in order to maintain the behavior that we want to be able to serialize accesses to any particular address such that all the processors see the serialized access, see the same serialized access to a particular address, right? And we said that you could implement cache coherence using a bus as a broadcast notification mechanism and snooping. However, snooping doesn't scale, and so what you'd like is something that scales, and sort of directory mechanisms are much more scalable. And so from a software developer point of view, the impact of cache coherence, shows itself up most in the ideas that you have full sharing, and that if you can kind of think about changing your applications such that you can reduce the full sharing, then potentially performance could be a lot better. And one way to kind of understand when full sharing is happening potentially is to use some of these system tools to analyze cache behavior. Okay, so now so first of all, I should ask, are there any questions about cache coherency? All right, so you certainly, there are some exercises in the assignment that cover this stuff. Yeah.
We talked about directory protocol, and then you had mentioned that you're going to track like the different caches which have caches, right?
Yeah.
The size of that would keep increasing
With more processing.
Yes.
Yeah, absolutely. And then you might have some other schemes for reducing that, but we're not going to get into those details. Other questions?
I was just wondering, in the benchmark example, why did Redis sort of started issuing better performance with increased cache line size?
It doesn't. It gets worse.
Okay. There was a U-line shape, so it was decreasing a little.
Yeah, so
X is latency.
so we're looking at miss rate, right? So you're saying, why does it go down and then up?
Yeah.
You tell me. Why do you think? Okay, so what do we know about line size and spatial locality?
Line size increases, spatial locality increases. So
Well, spatial locality is better exploited, and so the impact of that is
And then you have false sharing, which
full sharing, which is pushing things up, right? And so eventually, the improvements that you get from exploiting spatial locality are outweighed by the detriment of full sharing. Yeah.
Is 8 like the standard cache line size in most processors? It's like 64 or something like that.
It depends, but usually it's 64, 128. Cache line sizes have been getting longer over time. Yeah.
I was interested in, so going back to the directory-based validation protocol in NESI and NSI.
Yeah.
So were NESI and NSI primarily used in caches that didn't have, or nowadays that we have the L1, L2, L3?
Well, so the directory mechanism is somewhat orthogonal to the exact protocol you're using, right? It's just sort of a way of, I mean, you could still have modified, exclusive, shared, and the question is sort of when do you indicate to the processor that you should pay attention to a transaction, right? You could do it with a bus where everybody is snooping, or you could do it with a directory which has point-to-point messages and is more scalable. But you still keep the same states, right? Does that answer?
Yeah.
All right, so so let's talk about memory consistency, right? Which is the kind of other side of the coin of dealing with memory and multiprocessors. All right, so we talked about how loads and stores should behave. Intuitively, you want to return the latest value written, right? And we said coherence says we're just going to talk about a single memory location. Memory consistency says, what about the apparent ordering of reads and writes to different addresses by different processors? How should they be ordered, and how should we interpret the behavior of a program, a shared memory program that does this, right? Okay, so this is going to affect, how we interpret programs, what programs mean, right? And by telling us what is the allowed behavior of the memory system or the compiler and the memory system, and the memory system, right? And so it's important because the way in which you allow loads and stores to different addresses to be reordered is going to have a big impact on how performant our system is. And it's also going to affect, what I, as the programmer, can do to improve the performance of my program. Okay, so what are we going to focus on? So let's see. So why should you care? So if you want to implement a synchronization library, you really need to pay attention to memory consistency. And if you want to develop a compiler or low-level OS code, then it's important to understand about memory consistency. It turns out that if you are an application programmer who does most of their development using compiler, so sort of a high-level language programmer, or you are going to use kernel libraries or system libraries, then it's not so important to understand the details of the memory consistency model. But if you're a kind of a low-level system developer, like potentially the people in this class, then it's important to understand, right? So memory consistency, it differs from memory coherence because we're talking about multiple different addresses, right? So what the memory consistency focuses on is its reads and writes to different locations as observed by different processes. Okay? So coherence says, hey, eventually any writes made to a particular address will all be seen by all the processes in the same order. And consistency says, when writes to different reads and writes to different addresses get seen by reads from other processes. Right? So, said it slightly differently, goal of coherence is to ensure the memory system, behaves as if the caches weren't there. Right? So you imagine that any system that has has caches in the system needs to be coherent. Right? It's kind of fundamental. If you don't want to work with a system that's not cache coherent. But even if you had a system without caches, you would still need a memory consistency model, right? So even systems without caches need a memory consistency model because we need to define the allowed behavior of the memory system, whether or not there are caches in the system. All right, so to kind of give you a preview of what we're going to talk about, in a modern multiprocessor system, memory accesses are going to get reordered, right? And the main reason for doing that is to improve performance, right? But then the question is, so what does that mean to the programmer? If you're an application programmer, you probably don't care so much. But if you are a systems programmer or a compiler writer, then you care a lot, right? Because it's going to affect what you can do in your compiler. It's going to affect the behavior of your low-level system code. Okay, so let's define a few things here, right? So there are 4 types of memory orderings that we can have in the system, right? So, you've got a program that defines a bunch of reads and writes, loads and stores, and these happen in program order, right? And the question is whether the memory system maintains this program order or not, right? For any particular thread, it's going to maintain the program order. The question is sort of what it does to accesses from different threads, right? So, so you have 4 types of operation orderings. A write of X to a read of Y is called is write to read memory ordering. So that says that the write of X has to commit and change the state of the memory before the read of Y takes place. So that's a kind of write to read memory ordering. There's read to read memory ordering. There's read to write memory ordering, and there's write to write memory ordering, right? So the key thing, of course, is that X and Y are different addresses, okay? So these are the 4 types of memory orderings, and the question is sort of, what memory orderings are going to be maintained by the memory system. So, in order to, get our heads thinking about this, let's look at a very simple program. So initially A and B are 0, And on processor 0, we set A to 1, and then we print B. And processor 1, we set B to 1, and then print A. So why don't you discuss with your neighbor and tell me which one of these outputs can be printed. So I'll give you a minute to think about it. What do you think?
Any of them?
Any of them? Any of them? So we have option for any of them. Do we have another view of what could be printed? Yeah.
Is it just 1, 1?
1, 1. Well, I think that's possible. So 1, 1. What else?
0, 1.
Yeah, 0, 1. Can 1, 0 be printed? Someone said yes, someone said no. Yes? Well, not clear, but let's see. So let's put a double question mark by that. What about 0, 0? Is that permissible? No. Okay, so that's not. All right, so in order to kind of understand what could be printed, a useful way to think about it is in terms of happens before graph, right? So what's required? What has to happen before what in order to allow the output that you expect? So remember, when you are executing in a multiprocessor environment, the instructions of the different threads on the different processors can be interleaved in any manner in time. Okay? Now, on any particular thread, the instructions are going to be executed in program order. But when they get interleaved into the global order, whatever that may be, is going to be dependent on things that you can't control. All right? So let's assume that, that we want a particular output like 0, 0. Right? So that says that we would need to have the print of B happen before B gets set to 1, right? And we'd also need the print of A to happen before A gets set to 1. And we know the program order on any particular thread is statement 1 before statement 2 and statement 3 before statement 4. So we put those arcs in. And then what we have is a cycle, right? So we don't, so when we've got a cycle, we know that the outcome's impossible because an event must happen before it's held, before it's itself. And so that says we can't get 0, 0, and we can't get 1, 0. Yeah?
If you have a store buffer and you're like out of order operating and rearranging like a read to occur or a write, could you have 0, 0?
We'll see. That's a good question, and we're going to investigate that. All right. So, so the question is, what should the programmer really expect? Well, if I kind of asked you, given, what you know about shared memory so far, what you would probably say is, hey, there's some global ordering to all of the accesses in the system, and I want to respect that global ordering, and I also want to have a global ordering that everybody sees, that I can serialize all the accesses, memory accesses in the system, and also, of course, that global order would mean that any particular thread, the memory accesses are made in program order, right? So what you would be describing loosely is what was formally defined by Leslie Lamport in 1976 as sequential consistency. So sequential consistency, for which he partly won the Turing Award in 2013, basically says that all operations are executed in some sequential order, as if they were manipulating a single shared memory, and then any of the accesses or any of the operations in any particular the thread are always happen in program order. Okay? And so that means that sequentially consistent systems maintain all of the four memory ordering orderings that we just described. Write to read, read to read, read to write, and write to write. Okay? So we've got this sequential global order, and notice that this diagram slightly changed from the coherence example, in that we now have multiple addresses, X and Y, in the diagram, and there's some global order, right? One way of kind of thinking about sequential consistency is this switch metaphor, where you've got a single shared memory, you've got this pointer, and this pointer, randomly points to any of the processors, accepts a memory operation from the processor, and then flips to another processor and takes some random number of accesses from that processor. Okay, so we've got this idea of sequential consistency. So here's the picture, right? We've got A equals 1, R1 equals B, B equals 1, R2 equals A on processor 0 and processor 1. We start by executing a operation from processor 0, followed by an operation from processor 1, followed by an operation from processor 1, and then finally an operation from processor 0. Okay? So with a switch metaphor, then you can kind of look at the interleavings that you might get, and you would see, we go back, this is just another representation of that first example, that, both 0, 0 and 1, 0 are illegal. You can never get it from sequential consistency. Okay, so why might we want to relax these orderings? So do something other than sequential consistency. So from the point of view of a programmer, right, sequential consistency is the most obvious and intuitive thing, right? If I look at a program and I think about its multiprocessor execution, what I want to see would be sequential consistency. And the question is, why would any system implementer want anything else, right? And the reason is, of course, it's always performance, right? That's what this class is about, right? So we want to relax the orderings so we can get more performance. In particular, there was some comment about, hey, what if I had a write which was going to miss the cache and have to do all sorts of things. It's going to take a long time. Followed by a read, and maybe this read's going to hit the cache, right? They're two different addresses. They're unrelated. Why shouldn't I do the read before the write? Or at least maybe I want to overlap the two, right? So if you think about from the point of view of the application wants to read its data as early as possible, and who cares about the writes, right? You can push them off later or try and overlap them with other reads. Okay, so that would be the idea is that sort of why wait for the write to finish, which would be sequential consistency. Let's at least overlap and maybe reorder. Okay, so let's see what happens when you do that. Okay, so the problem with SC is of course that you've got this case where these two accesses are unrelated, and you'd like to have the read happen before or earlier than the write, because the write is going to take a long time. Okay? So somebody said write buffer. Good idea. Let's put a write buffer in, right? So the write buffer is going to basically say, hey, you write, you're going to go, eventually it's going to be sent to the memory system, but in the meantime, hold off, don't use the bus, don't use the resources, because I'm going to issue the read first, because the processor is waiting for the read, and that's gonna if I get the read earlier, then I will get better performance, right? So I'm going to put a write buffer in, and the problem with the write buffer is it's going to change my memory behavior. Okay? So in the case of can R1 and R2 equal 0, we said in sequential consistency that can't happen. So the question is, how could it happen with write buffers? You asked the question, so you tell me.
If you have the writes just sitting in the write buffers and then you go ahead and execute the reads while that's occurring, then you would read 0, 0.
Right. So in this case, you'd read 0, 0, and that's not sequentially consistent. It may not be obvious why this behavior should be. And the question is, okay, so I have a write buffer. We said the reason that you want to reorder things is to improve performance. This just shows you a couple of examples where you can get, performance improvement that's pretty substantial by having a write buffer between the processor and the cache. Or maybe you put the write buffer on the other side of the cache, between the cache and the bus. Okay? Write buffers are important. Every major instruction set architecture supports write buffers, right? And the problem is write buffers don't fit within sequential consistency. You need a weaker consistency model to have a write buffer and you want it because you want the improved performance that comes from that. But now you need a weaker memory model, one like total store order or processor consistency or partial store order. And in total store order and partial store order, you are going to relax the first ordering case, right? So write to read order. You're going to allow reads to happen in a write to X followed by a read to Y to happen in a different order. So total store ordering or partial store ordering, this should actually be processor consistency is actually something different, which is PSO. All right, and so now we're going to allow you to overlap the read with the write and somehow reduce the impact of the write latency. So hide the write latency, right? Okay, so total store ordering basically says total store ordering says processor can read B before it writes to A as seen by all the processors, and the processor consistency, I thought, I mixed them up. Sorry, processor consistency, I can't remember. Yeah, so I think, anyway, I'll get it right. I think this is right. Yeah. So this is the one that says, hey, you can reorder the writes and the reads. And the question, the difference between total store ordering and processor consistency is when everybody gets to see the stores. In total store ordering, everybody sees the stores in the same order. In what I thought was partial store ordering, some get to see it earlier. But anyway, I'll make sure that I actually, there is a joke that says something like, there are two hard things in computer science: naming things and and memory consistency. So this is the exactly. So anyway, all right. So coherency because we got caches. Consistency because we need to have a way of understanding what our programs mean. We can do things that are even more aggressive than allowing reads to bypass writes. We can reorder writes, and this is partial store ordering. And in this case, if we are protecting a change of a variable from a flag, we're trying to do synchronization, then things could get reordered, and our behavior would be not what we expect. Okay, so again, we're going to do this to improve performance. The way that we can get rid of them all. And by the way, who has a cell phone? ARM uses what's called relaxed consistency, right? So it doesn't have any of these orderings in its memory consistency model. And so how do you fix this problem? Well, you put fences in, right? How do you fix any problem in parallel computing? You slow things down, right? Locking is a mechanism for slowing things down. You tell, and fencing is even worse, right? So fencing says we're going to wait for the memory system to quiesce, right? And that everybody is going to make sure that their all the processes are going to make sure that they have issued all their operations before we allow any of them to go beyond the fence, right? So this is a hardware mechanism that gets implemented. Yeah?
Faster for some reason because of this, or is it just simpler to do this way?
It's both a simpler implementation and also higher performance. But it means from the systems programmer's point of view, it's more tricky to deal with. But the way to deal with it is to add fences, right? And you can have fences, you can have store fences and load fences, and this all gets pretty tricky. And refer you to lots of online documentation if you want the details. Okay, so the problem is data races is that you've got two accesses to the same address. At least one of them is a store, and you don't have any synchronization between the loads and the stores, and so you have an unsynchronized program. And whenever you have unsynchronized program, then you can get data races, and when you have data races, you can get unintended behavior. And so the question is, how do you make sure that you can run programs on a machine that doesn't support sequential consistency, but still have behavior that you can understand? You make them synchronized, right? So that's the whole idea behind to kind of data race-free programming is, don't write code that uses unsynchronized accesses to data. Whenever you've got shared data, make sure you put in synchronization, and then the people who actually write the synchronization libraries have to understand the memory consistency behavior of the underlying processor, and the people who develop the compilers have to understand these issues, but you as the application programmer can kind of just rely on the fact that somebody who's much more knowledgeable than you has done the right thing and given you a call that you can just make. Okay, so I think we're at time. So we're going to turns out that memory consistency really needs to be dealt with at two levels. At the hardware level, what the hardware provides, but also at the language level. So we'll say a few words about that next time. See you next week.